Hello everyone. We're going to start with section 2.5 now. Let's go ahead and get the chapter up. Remember the last set of slides we went through sections 2.1 through 2.4. And so here we are starting now with describing viscous effects. This is very important in fluids. This is an extremely important concept, and you will see this throughout the entire semester. So it's very important to understand what viscosity is before we move forward into talking about various equations that describe fluid motion, or fluid statics for that matter. So viscous effects in fluids influence the energy loss, drag forces, flow separation, and other important parameters in fluid mechanics, which we'll talk about as we go through the semester. So let's make sure we have this concept down before we go forward. Viscosity is given the Greek symbol mu, and it's a fluid property that describes resistance to flow. And it's described with this equation right here. The viscosity mu is equal to the shear stress divided by the rate of shear strain. The shear stress is given the symbol tau, and the shear strain, the rate of shear strain, is given it is just the change in velocity over a change in distance. So if you look here at the bottom of the graph here, you see a uniform flow encountering a flat plate, and in fact that plate has a pretty sharp edge to it here. And we'll see later on in the course how this develops a boundary layer around it. But for now, let's not worry too much about the details, but just imagine a uniform flow impinging on this plate and flowing over it. So what we see is that there will be a force, a shear force, caused by the viscous effects. And in this example, the shear force is the force of the fluid, the flowing fluid on the plate. So as the fluid flows across the plate here, it's going to enact a tangential force, if you will. And that force is going to be related to the viscosity. So let's take a look, as I go back here, let's take a look at both tau and the shear stress and the rate of shear strain and look at what they are. So the shear stress is pretty easy to understand. It's just the tangential force per unit area on a point. And so if we looked at a differential area, delta A, centered on a point on the surface of the plate here, the fluid would be enacting a tangential force, or a force along the plate as it flows past. And that force, that tangential force, the change in tangential force over the change in area is going to be what is the shear stress. And of course, we take that in the limit at a point on the plate, basically. So it's just a tangential force per unit area. That's not too hard to understand, although normally when we're dealing with forces, we're usually talking about normal forces, or forces that act straight down on a plate. But in this case, we're talking about a tangential force that acts along the plate. The rate of shear strain now is given by this formula here. The rate of shear strain is going to be, basically turns out to be the delta V, the velocity, change in velocity over the change in y in distance. And so what we see here on the left is a depiction of strain caused by a shear stress. And so if we imagine the fluid flow, the uniform fluid flow going across this plate here, which is this gray thing here, the fluid flow, turns out, we'll see here in a minute, the fluid flow has to go to zero at the boundary. And so this is actually a velocity of zero here. And so what's going to happen is, as the fluid flow moves across this plate, there's going to have to be some sort of velocity profile. Up here, we're eventually going to have the free stream velocity. That is the velocity, if I go back here, the velocity of this uniform flow before it encounters the plate. So if you go far enough away from this plate, the uniform flow will just be flowing at the rate it is right here before it encounters the plate. So so in this case, we can see that there's going to have to be some sort of profile. And if we start, you can see these, what we're doing is we're looking at two pieces of fluid, one at time t and another at time t plus delta t. And we're looking at how these, basically the fluid particle, remember we defined this in chapter 1, a fluid particle is a particle that maintains its character. It doesn't lose any buddies. It holds on to all its molecules here, but the thing can deform. And what happens in this case is under the action of a shear stress from above, and knowing that the velocity has to go to 0 at the boundary with the plate, we get deformation of the fluid particle. So we might, at some time, we might start out with a nice rectangular fluid parcel here, but at time delta t, we get deformation. And the deformation is going to be, the rate of shear strain is going to be basically this change in the change in the shape of the fluid, this delta nu, or this delta phi over the change in time. And through a bit of mathematics, which is shown in the book and kind of shown here, you can see that we can basically replace delta phi over delta t with delta v over delta y. So there's a little bit of mathematical trickery in here, but basically delta phi over delta t equals delta v over delta y. So the rate of shear strain can be expressed either as, kind of the deformation in time or the deformation in space, and that's what we choose to do in fluids, is to use dV dy. So this is a hard concept to understand, maybe mathematically, but it's fairly easy to understand in terms of what is actually happening to a particle as it moves, as it's experiencing this shear stress tau at the upper boundary of it, and a lesser stress at the bottom. So it's being kind of twisted, if you will, and it turns out to deform it. I guess there's kind of you can look at these two different triangles. You got delta y here and delta v times delta t here and delta phi, and by looking at the geometry of these triangles, you're able to get this relationship here. Note here that there's this statement here that says the rate of strain is the rate of change of the interior angle of the original triangle, or rectangle, sorry, which would be this here. So I think it's easy to understand in principle, and just to remember that that's what the rate of shear strain is kind of the fluid particle deforming in time when it's subjected to a larger shear stress at the top than it is at the bottom. I'm going to stop now and set up and do a couple of experiments that will show you this. I've obviously never done any experiments with the camera, but I'm going to try to now. So just hold on. I'm going to bring up the camera, and it should show you a stack of paper here. So what we have is a stack of paper, and I'm going to, I can enact a shear stress on this by pulling from left to right here. I'm actually just running my hand along the paper, but if I actually grab the paper and hold the bottom of the paper, watch this corner right over here. Watch what happens to the stack of paper when I drag the top of it. Let me see if I can do this. Basically, when I drag the top of it, I'm going to have to kind of pull it. But this would be kind of the way that, if these things were connected a little bit better, basically, by moving the top and by enacting a shear stress on the top of it here, and fixing the paper on the bottom by not allowing the paper here on the bottom to move, we're simulating what happens to a fluid, in that it shears and it changes, it deforms basically. So maybe that's not the best example. It's a little hard to show that. So what I'm going to do now, I'm going to leave one piece of paper here, or a couple pieces of paper, and hold on, I'm going to get some stuff here. So we've got some water in a baking pan, and I'm going to show you this from above. First of all, I'm going to just, before I do anything, I'm going to just put a drop of food coloring in there. It's very dense, so it should sink to the bottom. Maybe not. Come on, drop. There's not much in this. There we go. Okay. That was way too much. Well, that's going to be interesting. Yeah, so what I wanted to show, see if I can do this. You can see the drop fell down in the bottom of the pan. In fact, you can see it kind of smearing around a bit. Let me get down a little bit more. Most of it's laying on the top. I was going to try to drag this knife, basically this chisel, where is it? This chisel through there to simulate some shear stress. I'm basically going to drag this across the top and see if we could see the fluid change. I'm not sure. This is going to see if we could see the shear stress. I'm going to draw it over, so there's kind of a spot on the bottom now. You can see right here the spot on the bottom of the pan. That fluid, that food coloring has sunk to the bottom. There's a bunch of stuff on the top, but don't worry about that. And what we're going to do is as I drag this thing across, I'm going to drag this knife across the fluid here like this to simulate a shear stress at the top, and hopefully we'll be able to see what happens to that little drop, and it should shear. So let's give it a shot. I'm not sure how this is going to work out, but let's go ahead and drag it across. Try it again. So we can see it picked it up a little bit. It actually is just kind of making it turbulent. It's maybe not the best example, but the idea is that the fluid is deforming. You could kind of see that. It actually, instead of being laminar, it kind of just stirred it up and made it look turbulent. So let's just get rid of the camera here. Bear with me. Probably not the best example. So we're back to the slides. So what I was trying to show is I was trying to draw, basically I had some fluid, some food coloring down here on the bottom. When I put the food coloring into the baking dish, the food coloring is more dense, and most of it settled down into a blob down here in the bottom. Unfortunately, it was too large of a blob, and some of it stayed on the top, but there was a large blob of it here. And what I was trying to do was, when I drew that knife through the water, I was trying to simulate a pattern of shear stress in this way, to show that the food coloring would be drawn along the tank. And in fact, if you look at the tank, you can see that let's just go back for a second. If you look back at the tank now, you can see that drop has been kind of drawn out now. It's not all together. So that was the idea. So now we have kind of an idea of what shear stress is and the rate of shear strain. And so that is, as we saw before, that is what the viscosity is equal to. Shear stress over the rate of shear strain. And we can write the rate of shear strain as dV over dy. So we get a velocity profile now if we have fluid flow like this, we just saw, if we have a uniform flow going over a plate, we develop, instead of having a uniform flow like this over the plate, we develop a profile. And this profile, we're going to have various solutions to this profile depending on the conditions. We'll talk about that in a minute. But as I just said, we have what's called a no-slip condition at the plate itself. And this is very important. It says that the velocity of the fluid must equal the velocity of the wall itself, or the plate in this case. And since the plate is stationary, then this means that the fluid must also go to zero at that boundary. And we're going to go through a couple of solutions here in a minute of this. So the no-slip condition says that the velocity of the fluid in contact with the solid will equal the velocity of that solid. All right. So the viscosity causes the fluid near a wall to slow down, thereby creating the no-slip condition and the velocity profile. And the velocity profile causes a fluid particle to experience the shear stress, as we saw before. We're going to have the shear stress being in one direction on top of the parcel and in the other. But basically, these are kind of relative. It's kind of spinning or shearing the parcel. So our working equation here is that if we rearrange this equation that we saw before, the shear stress is going to equal the viscosity times the rate of shear strain. And for most fluids that we'll be dealing with in this class, and we'll talk about one a strange fluid in class, we'll talk about a non-Newtonian fluid. For most of the fluids that we'll talk about in class, they will be what are called Newtonian fluids, that the shear stress, tau, will be linearly related to the velocity gradient, dv dy. And the constant of proportionality is, in fact, the viscosity.